Now, as we move forward, it's time to dive deeper into the fascinating realm of quantum circuit compilation, one of the most crucial and intellectually stimulating areas in quantum computing. And for that, I'd like to call upon Nikhil Teja, our lead organizer, to introduce the guest to you.
So, hello everybody. Once again, we're going to start another session. So, I'd like to introduce Ms. Janani. Ms. Janani is a highly accomplished professional who has been deeply involved in advancing quantum computing technologies and developing innovative approaches to solve. And we are fully privileged to have with us exceptional experts. Janani, a quantum engineer at IBM Quantum Research, Bangalore. Beyond her technical expertise, it also enthusiastically building respecting quantum levels and for the contribution to broader quantum community through research, collaboration, and education initiatives. Anjali stands as an inspiration to all of us who are inspired to share the future through quantum innovation. So, with immense respect, let's Miss Sandy to the dais to deliver her message on quantum circuit compilation.
Connect the HTML. Connect the HTML to and then start. Yeah, I keep connected. Hello. Um, Firstly, thank you so much for the warm welcome, Nikhil. The aspect ratio seems a bit off. Can we, for the presentation, can you just get it to come in the center or have a seat? Great. Um, Firstly, hi everyone. I'm so excited and thrilled to be here. This is probably one of the largest audiences that I've had the privilege of speaking to. And more than that, the past day that I've been here, I've been able to kind of feel the enthusiasm that all of you have for quantum computing. And as someone in the field, this is truly heartwarming for me to see. So, let's get started with the session. And I hope. Um, you can take away from here and this fest and build forward and keep doing more quantum computing. So let's get started. uh, this is okay. Yeah, I can actually do this. uh, yeah. Okay, let's get started. First, I want to set the tone for this talk. Okay, I want to recount the words that Dr. Venkata Subramaniam he told us. I'm from IBM, by the way. So when he first told us about the news that quantum computer is coming to Amaravati, he used some specific words. He said the stars are aligning and the sky is the limit. So this is the replica of IBM Quantum System 2 at IBM Research Bengaluru in EGL. And basically, this is what is coming to your doorstep. So it's a dream that you guys will be having access to this. And the fact that, this kind of ecosystem is brewing here, there is so much interest for doing quantum computing. The fact that a quantum computer is going to come here, and yeah, this is basically stars aligning, and basically magical things can happen if we keep up the interest and drive ourselves forward to do something good. So I have a lot of expectation, and I think this ecosystem has a lot of potential to get things going. So with on that note, let's get started with this talk. So the vision of IBM Quantum, or yeah, let me where did I point it? Is it down? Yeah. Mm, yeah, great. Yeah. Okay. So I wanted to talk about a more like I wanted to pick a special topic for this audience, particularly because you will be having access to a real quantum computer. So this topic in particular, quantum circuit compilation, this is something very relevant and important to doing quantum computing on quantum hardware. Uh, like given the kind of discussions that go on in the community, there is a misconception that using simulators is the same as doing quantum computing, but that's not really the case. And one of the takeaways I hope we can have from this lecture is to know the difference between what it is to do real quantum computing on quantum hardware itself. So the mission of IBM is to bring useful quantum computing to the world. So, how can we do that? I will be touching a little bit upon that topic as well here. And I'd like to start with what the objectives and key takeaways for this session would be. Before that, I would like to say that for me, I'm okay with having a more informal session. If 70% of you guys are, comfortable with or comfortable and are able to take away at least 70% of the content that I'm talking about, that will make me happy. So my objective is personally is not to get to the end of the lecture, but whatever I'm covering, if you guys are able to understand that, that's more important to me. So at any point of time, if you have any questions, please feel free to put up your hand, interrupt me, and ask me any questions that you want to, ask. So for you guys, from this talk, what are my objectives in terms of the topics and what I hope will be the key takeaways are these three things. So what it means to do useful quantum computing, that will be the first one of the things that I'll be talking about. Then what it means to do quantum computing on quantum hardware and how it differs from using a simulator. Then, last but most importantly, after this lecture, you guys need to continue learning, right? So, this fest is an amazing way to kickstart this whole effort on upskilling you guys and getting you more accustomed to doing quantum computing. But the learning starts from here, and what can you rely on to give you that learning? So, we will touch upon a few resources that you can use to upskill and equip yourself in quantum computing after this talk. So, what does it mean to do useful quantum computing? To elaborate on this, I'd like to quote Jay Gambetta, an IBM fellow and the vice president of quantum computing. At that time, he was the vice president of quantum computing when he said this, but right now he's the director of IBM Research. And he said, I like to say, if you're not using 100 plus qubits, you're not doing quantum. So what does this statement mean? 100 plus qubits is a big number, right? Relatively compared to what we see today, and what like the highest number of qubits we have on, say, live quantum system as of now is with IBM with 156 qubits. So what do we mean by that? And I'm specifically talking about superconducting qubits. So what does this mean? Let us analyze that statement a little bit more. So there is a rich seam of problems that cannot be solved by classical and AI superconducting, and it never will be. So these are trillion-dollar problems that quantum computing was designed to solve. So if you look at the complexity of problems, you have hard problems which are NP complete. And then you have problems which are easy for quantum computers to solve, but not really for, say, the classical computing resources. And of course, in between these two, you also have easy problems which can be solved in polynomial time, which is what we use current day classical computers for, right? So what are these problems that quantum computing was designed to solve? So modeling molecules, atoms, electrons, and quarks with unprecedented accuracy. So this is basically a work which was done on the Heron quantum computer with 77 qubits, using HPC, basically the superconductor Fugaku at Riken, in order to achieve results which are comparable to the best classical approximate methods in both accuracy and timing. And as you see here, it took total of 12 minutes using 77 qubits and 1.5 hours of supercomputer time to get to be able to solve this particular very complex problem. So this is that is one of the example problems that quantum, and in more specifically, say, using methods such as quantum centric supercomputing, is it these are some example problems which are expected to be useful to solve using a quantum computer. You also have initiatives for developing lighter, longer lasting batteries for electrical vehicles. Then you have designing better materials for like, say, planes, ships, these kind of industries. Then you have discovering, basically, in healthcare you have drug discovery, which is again a very active field which is hoping to benefit from quantum computing. And you also have technologies such as renewable energy. So, to kind of put this into a more rosy picture, you have easy problems. So, if I asked you to do 10 into 3, are you going to pull out a calculator or write a sophisticated Python program? No, right? It's just mental math. You can do 10 into 3. It's very simply 30. So, if I want to do these kind of simple problems, I'm not going to use a calculator or a sophisticated Python program. Same way, you don't want to solve trivial problems using a quantum computer. And very often than not, going back to Jay's statement, you don't want to solve very simple problems using a quantum computer because it's an expensive resource and it can do much more than a classical computer can. If a classical computer can solve a problem well, you should use a classical computer for that. You should use a quantum computer to tackle more difficult problems that it is suitable to solve, right? So in that sense, there is a sweet spot between very easy trivial problems where you don't need quantum computing for doing tasks like arithmetic, or to build video games. So those are some easy problems for which you don't want to use a quantum computer. Then you have very hard problems as well, for which you need fault tolerant quantum computers, which means current day quantum computers are going to fall short on certain places to be able to implement the more advanced quantum algorithms. So for example, if you look at Shor's algorithm or Grover's algorithm, these are algorithms which require a fault tolerant quantum computer for several reasons. Firstly, you need high fidelity in terms of the computing, which means that the result that your result is of good quality and it is not too badly affected by noise. But also the algorithm itself. For example, if you take shores, to even factorize a very simple number, you need a high number of qubits to implement. Sorry, you need a high number of qubits, and you need to be able to implement gates of a higher depth. So in these cases, you need a fault tolerant computer which has a lot more, which is a lot more powerful as compared to the current day quantum computers. But we are in the utility era and we are going there. So what you're looking for as to when to use a quantum computer is the sweet spot of which is in between easy problems, easy or trivial problems, and very hard problems, which are going to take some more time to solve. In terms of the hierarchy, so what are the problems that we can actually tackle? We have solvable problems, we have interesting problems, but the ones we need to aim the most for are timely problems, which means you want to pick problems that are solvable, timely, but also of interest to solve uh, using the current existing quantum computers. And depending on which field this is being implement like which field it is being applied to, its success will depend on how using a quantum computer can bring value above what classical capabilities alone can achieve. So what are some of the industries where this is expected to have an impact? We have chemistry and materials, we have optimization and search problems, we have machine learning and AI, of course, and we have numerical simulations. So these are the sort of type of problems which fields or which industries it hopes to impact. You have aerospace, automotive, chemicals, electronics, and semiconductors. You have energy, financial services, and healthcare and life sciences, most importantly. So this is of course not an exhaustive list, but this is supposed to be representative of the wide and far reaching impact that quantum computer can have, and where we need to look for applications to do these things. So moving on from there, quantum must be performant and quantum must be easy to use. So, as we all know, quantum computing is not a very easy topic to start with because it's very multifaceted, right? You need knowledge of physics, you need knowledge of computer science, you also need knowledge of information processing, and you also need domain specific knowledge if you're looking at an application. I know this seems intimidating, but on one hand, while it is this way, if you look at it from the other side, people from computer science background can do quantum computing, people from physics background can do quantum computing. Say if there is a researcher in bioinformatics who has tried every possible avenue of research they know or that they are interested in to solve some particular protein folding problem, and they are not finding much success, and say they turn to quantum computing looking for a solution, they can also try to use quantum computing. So to make it more approachable, we need to make sure that quantum is easy to use, but we also need to make sure that it is performant so that it is actually useful. So one of the main offerings from IBM on the software side is of course Qiskit, which is I think accepted as the lingua franca of quantum SDKs. So for me also, like I think I personally in my journey I used MATLAB to write Grover's algorithm when I did my master's thesis. At that time, I think I had some I had my own understanding of what I thought quantum computing was, but it was only after I entered the industry and I came across things like Qiskit that I understood, how much more easy and how much more understandable. And you can actually use it like a proper brick or a building block to build up to what you want to implement. So in that sense, you have Qiskit, which sits in the software stack, area of quantum computing at IBM, let us say. So But where exactly are we using Qiskit? So to understand that, we first need to understand the anatomy of a quantum computing service. Now, this is very uniquely specific to how you implement a quantum program on a quantum computer. It's not unique to an IBM quantum computer. In general, the anatomy of any quantum computing service must have this kind of blueprint. So you have the user who uses a quantum programming language to write or say build quantum circuits. Then they send these quantum circuits using some kind of cloud service to some server in a laboratory. Okay, and this quantum circuit then kind of undergoes some runtime compilation and things like that. It goes through the control electronics and it gets converted to pulse sequences. Then these pulse sequences are what are actually implemented in in a quantum computer. If we go back a few slides and I showed you this, right? This particular this is of course a replica, but particularly the actual chip in the quantum computer is at the base. So this whole chandelier thing that you see, that is golden and very shiny, that is actually part of the refrigeration equipment. It's not actually the quantum computer itself. It's just the cooling apparatus that makes the chips stay at the temperatures required to maintain superconductivity. So in that sense, coming back to this slide, right? Uh, what actually gets implemented on the quantum computer are pulse sequences. So there are these many things going on when you are implementing something on a real quantum computer. And why do you need a cloud service? Because at this point of time, you cannot have your quantum computer on your lap like you have a laptop which is built on classical, hardware. Rather, you have a quantum computer located in some place, but you are still able to use it thanks to the cloud service. And this is what this is what the anatomy of that quantum computing service looks like. Now, here specifically, what is the, where are we talking to, or what is the scope of what we are directly affecting, or where we are talking to? It is in this regime where, as a user, you build, quantum circuits or whatever, and you send it through the cloud service. Here, specifically, Qiskit itself will be used here just in the first step to build your quantum circuit. So for IBM, you have something called as Qiskit Runtime, which performs this cloud service operation. And that is done using this SDK called as Qiskit Runtime. So now what is Qiskit? Uh, just to make put a formal definition to this. So Qiskit SDK is an open source SDK for working with quantum computers at the level of extended quantum circuits, operators, and primitives. So some of the operators and the like, which was discussed in the previous session, right? If you want to actually build an algorithm with that, you will have several components. You will have qubits which are undergoing measurement, and then you might take the expectation of some qubit states with respect to some observable. So yeah, observables, I mean, I'm not going to go into it now, but so these are things that you can do with Qiskit. So then of course you have Qiskit Runtime, which is a cloud-based service for executing quantum computation on IBM quantum hardware specifically. Then you have Qiskit patterns. Now, this is not Qiskit specific, but I mean, in the sense you can apply this to a general quantum SDK. But Qiskit patterns in particular is a framework for breaking down domain specific problems into stages so that you can run it on a real quantum computer. So, if I take some problem, right, say I want to solve the protein structure prediction problem and I want to run it on a quantum computer to solve and find the structure of the molecule. How will I do that? That's such an abstract thing to think of, right? But if you break it down in this using this Qiskit patterns framework, you can actually have a stepwise plan as to how to really implement this on a quantum computer step by step and get answers from it, and get the solution that you're looking for. So what is this? We will not do a detailed breakdown, but we will look at it in some more detail in upcoming slides. Then you have the Qiskit ecosystem, which is a collective, uh, It's a collection basically of software and projects that build on or extend Qiskit. So you have things like Qiskit SDK, you have Qiskit Runtime, you have Qiskit Air, and you have Qiskit add-on packages, which also form part of the Qiskit ecosystem. So to get started with Qiskit, right now you don't actually have the IBM Quantum platform itself is on IBM Cloud. If you want to, in terms of installation, you will need to install Qiskit with the visualization package, and you also need to install Qiskit IBM Runtime. And in terms of the, you need to have an account set up if you want to access the runtime service with a token instance and everything. So once you set that up, you are sort of ready to just start building a circuit and doing going forward. Now at this point I would like to make a remark. If you just want to test and understand how to use Qiskit, you don't necessarily need say to start in the beginning itself. You don't have to immediately implement things on quantum hardware. You can use Qiskit and Qiskit Air to just play around with the features and just understand things. But again, if you want to do useful quantum computing, at some stage you have to set up the service, because you can use the 10 free minutes to run your circuits on real quantum hardware. So for the Qiskit pattern frameworks, Qiskit patterns framework, you have four major steps. So you map a problem to the first one is to map your problem to quantum circuits and operators. So if I say I want to solve the protein structure prediction problem, I have to come up with a model for that problem and think about what aspects of this problem I am going to what part of this problem am I mapping to the qubits, what part of the problem becomes my observable or my Hamiltonian. So these are some things that you have to do in the very first step. Now, after you do this, the second step would be to optimize your circuits for implementing on target hardware. Now, this is why quantum circuit compilation is very important. We will come to this. As we go on, this is one of the things we'll mainly discuss. But after you optimize your circuits, the third step would be to actually execute on the target hardware. And the last step would be to post process your results and get the results back from the quantum computer. So, say to map a problem, what do we need to do? We start with a numerical representation and we map it to a quantum computing representation. After this, we choose a quantum algorithm to actually solve a problem. For example, for the protein structure prediction problem, if I map, say, the structural components or the geometry of like my molecule, say I'm picking some, lattice to be the template, I will map these structural parameters to the qubits. Then I will say that the energy of the molecule, I will build a Hamiltonian which represents the energy of the molecule. Then when I minimize this energy, I can say that the minimum energy configuration corresponds to the structure of the protein. So this can actually be solved using something called as VQE, because if you formulate it as an optimization problem, it doesn't just have to be VQE, it can be different things. But VQE is one of the algorithms that you can use. So then you choose the quantum algorithm and actually run it to solve the problem. But let's not focus on this. For me, I want to focus for this session on the first two steps. And for this, you can use in the first step, if you build any quantum circuit, right? In the second step, if you want to implement it on quantum hardware, you have to optimize your circuit. And optimizing a circuit involves quantum circuit compilation. So how is that the case? First, let's discuss very simply how you can build a circuit with quantum SDK. So these are the foundations of quantum programs, right? And these consist of operations, including gates, measurements, and resets that manipulate the state of the qubits. So anytime I want to go from, say, a problem to a solution, I want my input to encode the problem, and I want my output to represent the solution. So from how do I go from input to output? I have to evolve my quantum state. And that evolution can be done by using gates, right? And these gates, measurements, and resets, these help manipulate your qubits. So this is a very simple bell state circuit. You have a Hadamard gate, you have a CNOT gate, then you have a barrier, then you have two measurements on each of the qubits. Now yeah, I'm not going too much into detail on the basics itself because I think those are covered in other sessions. But yeah, how do you actually implement the circuit? This is the code. I have skipped the installation steps here. Maybe I can show it to you in like notebook later if we have time. But to build the circuit, you first have to install Qiskit, and then you have to import quantum circuit and quantum register from the circuit. Then you build your quantum register this way. And as you see, I'm applying, say, the Hadamard gate on 0th qubit in my circuit. Then I'm implementing the CNOT gate with 0th qubit as the control and Q1 as the target. Then I'm measuring all the qubits. And this circuit.draw of MPL helps draw your circuit in a matplotlib style, which looks more nice than just giving, say, print circuit. So now let us discuss how we will optimize circuits for target hardware. Now here's where quantum circuit compilation, or more specifically the IBM term transfilation, comes into view. Let us discuss that in a little bit more detail. So, how do you optimize your circuits for implementing on hardware? There is an absolutely necessary and required condition for where you have to transpile your abstract circuit into a circuit that can run on target hardware. And then there is an optional step as well where you can verify your circuit with simulations. Excuse me. Any questions so far? But am I, for just to, like, is this a bit too I'm trying to keep this a bit high level, or is this like is whatever I've spoken so far, has that made sense, or do you have any clarifications about what has been discussed so far? Is it clear? Okay. So, but first of all, why do we need to transpile an abstract circuit? This is because real quantum hardware comes with a few constraints, and your abstract circuit needs to satisfy these constraints if you want to actually implement the circuit on your target hardware. Now, what are these constraints and where are they coming from? So, firstly, when you build a quantum computer, you cannot put every gate imaginable to be operable on that quantum computer. Instead, we have something called as a basis gate set, which contains a specific set of gates that can represent all possible quantum gates that you can come up with. And so, only a limited set of gates can be executed directly on hardware. Others will be rewritten in terms of these basis gates. So if I have a 3 qubit gate, 4 qubit gate, 5 qubit gate, which I can potentially have, I will decompose these gates in terms of 1 qubit gates and 2 qubit gates. Particularly, I will decompose them in terms of these basis gate sets. And one remarkable thing is that different types of hardware will have different set of basis gate sets. Not every kind of hardware that you are using will have the same kind of basis gate set. For example, some Eagle architectures which existed, Eagle architecture refers to some IBM quantum devices which used to have 127 qubits. Um, these used to have ECR gates, which are a kind of 2 qubit gate in their basis gate set. Now, the IBM quantum system 2 that we saw, these are based on Heron architecture, and these will have CZ gates. They don't have ECR gates. So that's just an example of how. Now I will show again in further slides the difference as well. But yeah, so the kind of gates that are there in your circuit, ultimately when you're running them, has to match the basis gate set of the architecture of the quantum device that you're running on. Now after this, there's a more tricky kind of problem with in terms of qubit connectivity. Now, when I'm writing this circuit, right, here I've put Q0 and Q1, which is the 0th qubit and the first qubit. But I can also potentially make a 120 qubit circuit and say that I want to put a C0 gate between the first qubit and the 120th qubit. Now, this is just me writing some gate, right? But how will I actually implement this? If I want to put a C0 gate between the first qubit and the 120th qubit, how will I actually make it happen? So if you look at here, this, I'm just zooming in a little bit. So this represents basically the structure of what your quantum computer looks like. This is particularly called as the coupling map. Okay. So this shows which qubits are connected to each other. I think it is intuitive, but we don't really think about this fact that not every qubit in your quantum computer is connected to each other. So some have specific neighbors and others are not really connected. And so if I have to implement a C0 between, say, the 0th qubit and the 120th qubit, how am I actually going to make it happen? So one way we do this is to firstly pick the layout of my circuit itself. Layout here refers to um, if I start with say 120 qubits, it's not compulsory that I have to always map the 0th qubit of again, a couple more terms to introduce here. We have something called as an abstract circuit or a virtual circuit, and we have something called as a physical circuit. An abstract of virtual circuit refers to a circuit which you just write using, say, Qiskit. But a physical circuit is one which has something called as a layout, and it is something that actually is implemented on a quantum computer. So you can, so to form a layout, you can map the 0th qubit of your quantum circuit to say the 10th qubit in the hardware itself. So this is, I mean, yeah, so this represents the layout of a quantum circuit. And to circumvent this qubit connectivity problem, one thing we do is to firstly pick a layout itself, which will facilitate, applying a 2 qubit gate. Now, one more thing here is that because this connectivity constraint is there, you cannot directly implement a 2 qubit gate between every possible qubit. Based on the hardware you have, you can only implement it on certain, implement it across certain pairs. Okay, but the way we work around this is to implement swap gates. So say I cannot, directly put a 2 qubit gate between 0 and 120. I will keep swapping 120 with, like, its different neighbors by applying a swap gate until, I reach a neighbor, and until I can swap that 120 qubit with a neighbor of the 0th qubit. This is a crude explanation, but what we are doing is going to be inserting swap gates similarly, right? Until you can actually implement the gate. Then we implement the gate and do the computation accordingly. Now, aside from this, the other constraint that you have to consider is the error. Now, in a quantum computer, not every qubit is going to be at 100% quality, right? Some days, due to some calibration errors, one particular qubit may malfunction. Now, if I'm running a 10 qubit circuit, there's no necessity that I map my 10 qubits to 10 faulty or error filled noisy qubits. I can map it to the best quality qubits available based on the qubit connectivity constraint, right? So, in that sense, you also want to optimize your circuit so that it kind of tries to avoid these noisy qubits. That was a lot of explanation. So let us take look at some illustrations. If you see, like, so this is a very sort of like, this is a very direct kind of view of what a quantum computer can look like. But if you actually look at its structure, it looks something like this. So you have 0 connected to the first qubit, then to the second qubit, third qubit, but you don't see any connection between 0 and 3, right? So if I want to implement a 2 qubit gate across 0 and 3, there are some tricks that I'll have to employ to be actually able to do that. And furthermore, you see, not all are colored the same way. Some are darker in color, and some are more purple, and some are very light. So the very light colored qubits are very noisy. so in representatively, and the dark colored qubits are they have good quality. So yeah, this is just a representation of what. And aside from this, you also have the fidelity of the gates that you have in between, right? Not every 2 qubit gate connection also needs to be good. It can differ across the board. So this is what physically, looking at a like a quantum computer on a program can look like. And very often, at least for transpilation, all this data is encoded using a programming object called as target. Yeah, so this is a more advanced concept, but so I will kind of just talk about it on a high level. But again, coming back to representatively talking about things, right? So um, to have a more realistic understanding of what we mean by hardware constraints, let us take an example circuit. Okay, so this is Hadamard, and then I have three C0 gates. This doesn't represent anything. This is just like a random circuit that I came up with. Okay, then I have a NOT gate on the fourth qubit, and then I have an RZZ gate on the third and fourth qubit. Now, yeah, this is a rotation, 2 qubit rotation gate in some sense. So if I want to implement this on, now this is just my abstract or virtual circuit. But depending on the hardware I'm implementing on, this is what the circuits can look like. As you see here, you have X gate, which was there in your previous like diagram also. Then you have RZ and square root of X gate. But then you have C0 gates for 2 qubit gates here, right? And this is for another different backend. And here I have ECR gates for my 2 qubit gates. And I have more RZ, I have square root of X, I have one X gate, yeah, and so on. Now, this is another sort of again, like this is another decomposition of the same circuit. As you can see, still has ECR gates, but in this case there are several more qubits or several more gates, sorry, not qubits, several more gates which are required on this circuit as compared to this, right? And again, this is another different decomposition of the same circuit. And as you can see here, this is the CZ gate. And again, this decomposition is looking different. But this circuit and all these four different circuits, they are all equivalent. They are just rewritten in different ways. Now, if you see here, there is a Q4 and an arrow to 56, Q3 and an arrow to 57. So this is what I mean by the layout or the physical layout of a or the layout of a physical circuit. This represents the mapping of your qubit, 2 qubits on the hardware itself. So what this means is that the fourth qubit on that abstract circuit is mapped to the 56th qubit on the device, third to 57th, 0th to 58th, and so on. So yeah, if you see here, like you can see the virtual like circuit qubits and the qubit on the hardware that they get mapped to. And here you see 0th is mapped to third, 1 is mapped to 2. So the order isn't really necessarily strict, right? But again, as I'm emphasizing that all these circuits are equivalent. So what is the difference between these four circuits and why do they look different? Now, the first circuit has been transpiled on IBM Hanoi, which is a 27 qubit device, I think. So, it's an old retired device. It's no longer online. But if you look at the basis gate set of IBM Hanoi, it has C0 gates and some of the other gates that you're seeing here. So, that is why when we had to implement this circuit, it got decomposed into this particular pattern. Now, this is again this the second and third are both transpiled actually on IBM Brisbane. So that is an Eagle device. But if you look at the starting layout which we gave here, it has 58, 59, 71, 56, and 57. And here the layout is 0, 1, 2, 3, 4, which is a trivial layout. Okay. And the thing is, as you can see, the trivial layout requires a lot more quantum gates to be implemented as compared to this particular layout. So it's always good to use lesser number of gates when you're implementing a quantum circuit than more. So in that sense, here by just changing the layout, you're able to use lot less number of gates to implement this quantum circuit. So then finally, this is a circuit which is transpiled on IBM FEST, which is a Heron device, and it is an IBM. It is yeah, it is the kind of like device that will end up coming here, coming to Amaravati. So here, if you see, you have CZ gates in the basis gate architecture set. Sorry, you have CZ gates here, and the reason for that is because in the basis gate set of IBM FEST, you have CZ gates as the 2-qubit gates, and in the previous case, you had ECR gates for 2-qubit gates in IBM Brisbane. So that is essentially why this is looking different. So now to further build on this topic, if you look at these two cases, now why are they different? One of the reasons is because if there is no physical connectivity between two qubits, but I am putting a 2-qubit gate between them, I'll have to add additional swap gates to make it possible. So, yeah, this is something we discussed earlier on also, right? So, the solution in these cases to if I have to apply a gate between qubits without connectivity at hardware level, yeah, it's to apply as many swap gates as needed to move the qubit state, implement the operation, and revert the state back. So, say yeah, this is just a simple, C naught gate run. Yeah, so this is a simple C naught gate run on a simulator, but I'm using a specific backend, and this is just to show if I have to implement a C naught between 0 and 2, where there is no connectivity between 0 and 2, then I'll have to swap 1 and 2, implement the C naught, and then swap it back. So if you see here, these two are the same, but implementing this will be a lot more expensive than implementing this. So that's the idea. It's you can implement these swap gates as discussed here, but it's going to be expensive to do so. The reason for that is one swap gate on, say, this is on a IBM Hanoi like architecture, that one swap gate is equivalent to three C0 gates, and three C0 gates on a say a Heron is equivalent to this circuit, and on Eagle it is equivalent to this is just a single swap gate, right? So you can see how expensive this can get. So that is why as you implement it, you want to minimize the number of swaps. Now, this whole optimizing the circuits to run on hardware is looking super complicated and very kind of involved, right? That is why we have yeah, so this is just again representing that this is transpiled on Eagle and this is transpiled on Heron. So the challenge is to run an abstract circuit on a specific quantum device. The solution is to do transpilation or quantum circuit compilation, where you convert an abstract circuit into an ISA or an instruction set architecture circuit. So if you have a simple Hadamard and a C naught and then a reversed C naught, the transpiled circuit is going to look something like this. It will have a physical layout. It will be decomposed into the basis gate set of the device, and it will also be optimized such that you're implementing as less gates as possible. So how do you actually write the transpilation? It's very simple. Once you have the circuit ready, you have to initiate a backend. Backend is a sort of, it's the representation of the device which you want to run your circuit on. So you get the device you want to run it on using the Qiskit runtime service. Then you initiate a pass manager object. Then you use something called as a with using basically generate preset pass manager, which is a which creates a default or or a very simple sort of pre-made pass manager to transpile your quantum circuit. So use generate preset pass manager, set an optimization level. We will talk more about this parameter on upcoming slides. You pass the backend argument and it will transpile the circuit for you. Basically, you say ISA circuit is equal to pass manager dot run of circuit, and you get the output ISA circuit as the transpiled circuit. Now this is ready to be implemented on quantum hardware. Now, the reason again I chose this topic is because any circuit that you're going to come up with for any algorithm is going to have to absolutely go through this step if you want to run it on a quantum hardware. So what are the stages? So since there's so many steps involved, we can come up with a more we can come up with a way of implementing it in a planned manner. So, talking about transpiler stages, you have initialization, you have the first step initialization, then you have layout, routing, translation, optimization, and scheduling. Now, what are each of these first steps? Initialization is to prepare your circuit for transpilation. So, say if I have a 4 qubit gate or a 5 qubit gate, you right away know that you cannot directly implement this because in general the basis gate architecture set of a quantum computer is only going to have single qubit and 2 qubit gates. So if you see anything more than a 2 qubit gate, the first step you will do is to decompose that into single and 2 qubit gates. So anything with 3 or more, you decompose it into 1 or 2 qubit gates in the initialization step. Then during layout, the abstract qubits will get mapped to physical qubits on the device. Then this we already spoke about, right? Then to actually make it implementable to make the 2 qubit gates implementable. Now again further in this step is routing, where you may want to change this layout you started with to minimize the number of swaps you have to apply so that you can implement all 2 qubit gates. Now, after this will be translation, where you change all the existing gates to the basis gate set architecture of the device. Then the final step is to do optimization, where you rewrite the circuit to minimize its depth. So basically, you do things like synthesis. So for example, if I have two C0 gates, right, I implement a C0 between 0 and 1, and then another C0 between 0 and 1. This is effectively an identity operation. Basically, nothing has happened on the circuit. Now, instead of implementing this on the hardware, put a C naught and then put another C naught and see that it's going to be identity, it's better to just do like, join these two in the transpilation step and make it to be identity so that you don't have to actually implement it on the quantum hardware. So these kind of optimizations are done in the optimization step. Then you have something called as scheduling, where this is a very kind of temperamental part of the transpilation. Now temperamental not because it's not a good operation, but rather you don't use it all the time. You only specify it if you want to do some advanced tasks. So this scheduling will introduce, say, delay instructions into different qubits to control the timing at which you implement the quantum gates. Okay, so now I'm going to skip this slide because this is again more detail on each of the transpilation steps, which I've already discussed. A little bit on the pass manager. So the pass manager is, say, the unit of doing any transpilation step. It's like, so if you look, so there is another thing which we call as passes. Now passes are, say, unit of doing some operations on the circuit. Okay, more specifically, it's the representation of circuit in a directed acyclic graph representation, or a DAG, which I'm not discussing here. But pass can do a specific operation on your circuit. Say here, I just want to, I have a condition where I want to remove all the if I have redundant C naught gates implemented, I want to remove all redundant C naught gates. Then I can create a pass for doing that and run that on the circuit. Now, to do the entirety of the transpilation, I'll have many such passes. One will decompose all multi-qubit gates. One will, kind of pick layouts for the given circuit. So, like, if I have a collection of all of these, how will I actually run it on the circuit? That is using this pass manager. So it manages passes, right? So I'm just maximizing the diagram a bit. So you see here it says pass 1 is to unroll bases, pass 2 is to cancel redundant gates. So multiple passes can exist, and each pass does one small well-defined task. The pass manager is going to manage all the implementation of these passes one by one, and manage how the circuit evolves through the transpilation process. And it does this by maintaining a global context about the circuit as it runs through this sort of pipeline. Okay, So I've included a source here. This is an excellent video, and it's one of the more advanced, lookups on transpilation. Now, this is going to be at a more lower level than what I'm talking about today. But it's if you're interested to learn this in more detail, this is an excellent resource. Okay. Now, some key concepts to keep in mind here are, DAG, which I mentioned, directed acyclic graph notation. Now, I'm not covering all of these because they are all, programmatic and a bit more lower level than or more detailed discussion than what I wanted to touch upon today. But you have the directed acyclic graph. Then you have something called as a coupling map. This coupling map tells which qubits are connected to each other in your backend. And again, the third one is a backend. Backend is the, data which represents all the information about the quantum computer that you are running your experiment on. Which qubit is noisy, which two qubits are connected, how long does it take to implement, say, a CX gate, or say a CZ gate on this across these two qubit pairs. So all this kind of information, right? So target, okay. So backend and target. Backend contains some of the more hard coded information. Target contains information that the transpiler needs. Okay. So yeah. So the instructions, the timings, the error rates, these are encoded in the target rather than the backend. So that is, I know I'm kind of, it may seem like I'm throwing some jargon here, but just stay with me. And then we discussed briefly about passes and pass managers. There's also something called as a staged pass manager, which you can look into. Then you have different transpiler stages, of course, which I just touched upon but didn't talk deeply about. You can learn about each of these in more detail because there are specific algorithms to do different tasks in these transpiler stages, right? So, for example, for layout and routing, we have an algorithm called as Saber. Then for optimization, we have one qubit peephole optimization and two qubit peephole optimization for reducing two qubit gate depth. So there are several. Then for layout, you have something called VF2, which looks at subgraph isomorphisms. So yeah, there are a lot of algorithms which come in here also. Now, briefly touching upon these, what happens at sorry. Okay, so I'm just briefly going to touch upon this optimization parameter level alone. So if you remember here, I said you have to set an optimization level, right? So if here it can take values 0, 1, 2, 3. Now, what is the difference between setting 0, 1, 2, or 3? That alone I will discuss, okay? So if you set to 0, what happens? So no optimization is happening here, but it is only like making the circuit ready with the minimal requirements for making it run on hardware, and that is done via basis translation. What is basis translation? Basically translating all the gates in your circuit to match with the basis gate set architecture of your circuit. So that is called as basis translation. Then you have minimal, again, layout or routing, which is done using the trivial layout, where if you have put 0, 1, 2, 3 qubits, it will be mapped to 0, 1, 2, 3 physical qubits. And of course, if this is a sort of very minimal work on layout, you have to put more swaps to make the gates work. If there are gates in the circuit which connect unconnected qubits on your backend. So this is what happens at optimization level 0. At level 1, you have very light optimization, where for layout routing, you put in a little bit more of effort. So you attempt to do it with trivial layout, and if additional swaps are required, you use some Saber swap methods, and then use some VF2 post layout to select the best qubits in the graph. Then you do something called as inverse cancellation, where, say, if I have two C naughts, or if I have an like a gate and its inverse, I will cancel those two gates instead of implementing them on the quantum computer and doing a null operation. Then you just do one qubit gate optimization. Then at level 2, you do medium optimization, where you have some more, advanced, layout routing mechanisms, and you have additional uh, additional optimization steps called as commutative cancellation. Then at the higher optimization level, you have further more steps to optimize your circuit more heavily. I'm skipping these details because it's going to be a bit of jargon, but basically level 3 you do very high amount of optimization compared to level 0, 1 or 2. Then some additional tools for transpilation. You can use the Qiskit transpiler service. But aside from this, you have things in the Qiskit ecosystem as well. You have things like the circuit netting toolbox. And aside from this, you can also write your own transpiler plugins. If you want your circuit to be implemented on the hardware in a specific way, you can write your own transpiler plugin as well. Okay, so now we are back to where we started, where we spoke about how to optimize your circuits for implementation on hardware. And an optional step was to verify your circuit with simulation, right? Again, we emphasize a lot that you are not using a simulator to do quantum computing, but to verify some things about your circuit and to see if it is ready for implementing on quantum hardware. While it is expensive to implement on quantum hardware and you have simulators for free, you don't do any real quantum computing with simulators because they are still pseudo random and based on classical architecture, right? So so if I want to say the problem specifically with using simulators again is that the runtime cost of simulating these quantum circuits will scale exponentially with the number of qubits. So for if I go at some point, if I want to go from 21 qubits on a like on a uh, classical computer versus on a quantum computer. On a quantum computer, if to go from 21 qubits to 22 qubits, I need one additional qubit. Whereas on a classical computer, I need 2 to the power 21 extra bits to go from or yeah to to go from these many circuits to sorry to go from 21 qubits to 22 qubits to represent on a quantum computer. I think I did the math right, but it's essentially a large number. Let's just keep that in mind. Okay. All right. So to conclude in terms of the differences, and again, one more point here, we spoke so much about transpilation. If you want to run a circuit on a simulator, you don't even have to transpile it. You can just run it like that. While it seems more simple, it also limits the scope of, what can be done on a real quantum computer, right? Because some properties, so in terms of the representation of a quantum system or a quantum state on a classical computer, it is limited as to how it's limited as compared to how you represent it on a real quantum computer. And the bigger problem is that it cannot represent the intrinsic quantum nature of quantum systems since it's based on a classical computer. And thirdly, the practical difficulty is that it will not scale to do useful quantum computing. Now, yeah, this is just the conclusion of this part. The last part we will discuss about how you can upskill and do quantum computing. Before that, are there any questions? Please feel free to ask anything. Like you don't have to feel inhibited. But yeah, if you have any questions, feel free to ask. Okay, so this is the last part of the talk where we are discussing how you can upskill and do quantum computing, even after this fest, and just to, or maybe as part of your career, right? So I would like to refer you all to the IBM Quantum Learning Platform, where you have several courses offered for free. You have tutorials offered for free to learn the basics of quantum computing and how to solve real world problems on IBM quantum systems like real quantum computers and using services. So this contains things like, courses, tutorials, and educational resources by leading quantum experts. So this is what the platform looks like. And yeah, you have several courses like quantum computing in practice. You have basics of quantum information, basics of quantum algorithms. If you want to do the the simplest courses to start with, you don't understand anything about quantum computing, I'll say that you guys should start here. Okay. So aside from this, I would also like ask you guys to be part of the IBM quantum community and interact with the IBM quantum community. Given that the fall fest is happening here, I would say that you already are part of the community. So here you have things like the IBM quantum learning platform, you have Qiskit advocates. Again, many of them are coming here for the talk itself, so there's that. Then I would implore you all to participate in Qiskit Global Summer School every year. It's great for several reasons, right? Now they have made it such that so participating in the summer school is a pipeline into becoming a Qiskit advocate now. So there's that. And really, most importantly, the latest features which are developed in a year, you will likely see something about that in the Qiskit Global Summer School. Whether it's like the latest algorithms, the latest, say, features like dynamic circuits, all of these will appear in the summer school. So, irrespective of whether you're a student learning quantum computing, whether you're an experienced person in quantum computing, or even an employee like me, I would participate in the Qiskit Global Summer School because it's such a great way to stay up to date with what's the latest thing happening with Qiskit. Okay. Then aside from this, you have things like the Qiskit YouTube channel, which is again a great resource. There are discussions on papers, discussions on new features, how you can use, something how you can use the latest features to do coding, etc. So then you also have the Qiskit developer certification, though I think there are some changes going on there. So yeah, just keeping that aside for now. So apart from this, there's also the IBM Quantum internship, IBM Quantum summer internship program, which where you get to work across the entire IBM Quantum team, from programming to materials research on real projects that matter. And the applications are open now, I think, and they're open in the fall and continue through the winter for different roles globally. So if you guys, yeah, this is just a picture of us with the interns from this year. Uh, so yeah, like I would ask you guys to apply for the internship program, learn on the IBM Quantum platform, be a part of the IBM Quantum community. And again, not pictured here, but Qiskit is open source, right? Qiskit is open source. Qiskit Runtime is open source. Even if you're not starting contributions like be in the beginning itself, I would really ask you guys to upskill more in languages like Rust. I don't know if you are aware of this, but like a lot of the functionality of what goes on under the hood in Qiskit is being transferred from Python to Rust, because Rust is more efficient and performant in terms of it's more performant and efficient as compared to Python for what is needed to create a quantum SDK. So upskill yourselves in Rust and learn about how open source contribution workflows happen, how GitHub works. These are all some things that you can learn today and learn right now to equip yourself, so that in the future you can, apply for, say, quantum software developer roles. This is not just going to be useful for you if you want to apply to IBM, but to any, quantum software developer role that might be open across the globe, right? So yeah, I have looking at the kind of interest that is there in this ecosystem, I have a lot of expectations and hopes for this place in particular. So thank you for your attention. Thank you for being here. Thank you for having the Qiskit Fall Fest. Thanks to my other co-speakers as well for being here. And thank you all. Finally, any questions? Okay.
Hello, ma'am.
Yeah.
Actually, I got a question.
Yes.
My question is from the initial steps actually.
Okay.
So you actually mentioned to predict the protein structure, it is required 77 qubits and 12 minutes of time and
Right.
1.5 supercomputing time,
Yeah,
right?
yeah, yeah.
And even after using 77 qubits, we only able to get the output as unprecedented accuracy. So my question is, why do we only use 77? Is the 77 qubit figure is the maximum that we can use, or like only available qubits are the 77 to get the unprecedented accuracy?
No, no. So this is a very problem specific thing. Okay. So I was
Yes.
just referring to the work that was done as part of a specific paper. So you can look at this. This is this is the work from Riken in collaboration with IBM Quantum. based on this algorithm called as sampling based quantum diagonalization, SQD. So yeah, so this is again like a ground state solver sort of use case where they are using SQD to solve the ground state of that molecule which was represented, and for that they needed only 77 qubits. Okay, so it's more like that particular problem which they picked needed only that much amount of qubits and resources specifically. So if you want the details, I would ask you to go back to that paper and read through the details, because that will clarify, I think, the specific questions that you're asking, why these many are being used and the like. So if you're using a different molecule, you'll need different number of qubits. So yeah, it'll vary a little bit across the board based on that.
So if I directly use more number of qubits than the required amount, I'll be getting the most
No,
accurate.
it is as many required. I wouldn't say it's
Okay.
more than what is needed. It's, yeah, to allocate. So in general itself, you want to, unless you're having some kind of an ancilla or whatever, you're going to be using only the kind for your particular problem. You will be using, at least in your problem mapping, you will be using only the number of qubits that you need. So okay, I can give you a trickier answer. The thing, but like simply answering it is that for your problem, you only need to use how many ever qubits you need. But when you transpile, your transpile circuit will have all 127 qubits. However, they will be idle because they're not doing anything, right? So if you, so part of transpiling your circuit is, and the requirement of an ISA is that it needs to match, your circuit needs to match the number of qubits which are there on the back end, because you cannot, if you have a 127 qubit device, it's not a 127 qubit device if you're only running 66 qubits, like switching on or something. That can't happen, right? You'll have all 127 qubits. Some will be idle, some will like have the computations going on. So in that sense, do we use only the qubits we need while mapping or encoding a problem onto a quantum circuit running on a quantum computer? Absolutely yes. Shortly, that's the answer.
Okay, ma'am. Thank you.
Any other questions? Okay.
Ma'am, whatever the transpilation you're talking about is automatic, or you recommend manual transpilation?
Oh, that's an excellent question. You will want to do manual transpilation if you need to do it. Okay, say I'm coming up with a different method to say I come up with a new novel algorithm to efficiently map my qubits onto the hardware, right? So basically, say I'm coming up with a new novel layout finding mechanism. Then I will have to write my custom. I can write a custom pass where I'm just using the layout part using my my pass. I'm doing the layout part of the transpilation using my pass, and the rest of it can be using Qiskit's default mechanism, right? So you want to do manual transpilation for specific tasks. Otherwise, you can just use the pre-built one, because that gives you like help on what you need. But say other things, like if your circuit is very going to be very heavy for how many C knots are there, then you can optionally say just run the C knot, like say a commutative cancellation step. You can run that multiple times to optimize your circuit more heavily for doing that particular task. So the way the transpiler architecture is built, it's very supportive if you want to do it manually and have fine grained control over different steps of the transpilation process. But if you're just like, I don't care about transpilation, I just want my circuit to run on hardware, you just use the generate preset pass manager to come up with your sort of default pass manager, which, yeah, and even there you have some knobs, right? Do minimal optimization, do maximum optimization. So yeah, by that way you can just use that if the scenario is the latter. Yeah. Thank you for your question.
Ma'am, quantum computing is mainly focuses on better optimization and simulation, right, ma'am? Yeah.
Simulation and optimization are two key areas where we are looking at quantum advantage or benefit in using quantum computing. So part of that is when Feynman first thought of why should we have, like when Feynman first had an inception of the idea of quantum computer, he said classical computers cannot sufficiently represent quantum mechanical nature. So I cannot simulate quantum systems on a classical computer. So perhaps if I had a quantum computer, it could better represent a quantum system than a classical computer can. So that's why simulation problems are some of the most important problems we want to approach using quantum computing, because there is a very good affinity in terms of the problem like pattern. Okay, but for optimization the answer is a little bit different. So that you can give two answers for the optimization from the optimization point of view. One is that quantum computers or quantum computing in general can encode more hidden or more complex sort of patterns and correlations between different qubits than classical computing can. Why? Because if you just think about it intuitively, right? In a classical computer, you have bits where you have 0, 1, where they can be 0 or 1. But in a qubit, you can have something in between a 0 and a 1, right? So it can encode more information, and more information could potentially translate to more complexity. And if a problem itself by its nature is more complex, there is a better chance of that showing up in a quantum computing based approach than a classical computing based approach. So that is one of the reasons why optimization is a good problem to approach using quantum computing. The second, I think, answer where why suddenly people started solving all optimization problems using quantum computing. One of that is because of this really great paper, which I personally really like. It's called Icing Formulations of Many NP-hard Problems, where several NP-hard problems are, you show that like many QPO problems can be rewritten as quadratic, like you can basically map it to an Ising Hamiltonian, and using an algorithm called VQE, and of course there are others, you can solve for these, you can minimize um, you can write it, make it into a minimization or an optimization problem, solving this Ising Hamiltonian, which corresponds to the QBO. Okay, so many graph optimization problems, the traveling salesman problem, which, for example, the protein structure prediction one, which I talked about, can be translated into an optimization problem. So many problems have this particular structure. So in that sense, it becomes a good sort of thing to approach. And because it's NP hard, it's hard to solve classically. And if quantum computers can solve that, we absolutely want to, use that, and, try to. It's one of the other avenues where quantum is doing something that classical cannot. So again, why you want to look at optimization problems?
Ma'am, another question.
Yeah.
There are a lot of GPUs and TPUs are building in the future also.
Mhm.
Is there any applications where we can't use it in the classical and can be solved in the quantum only?
Right. Okay. I'll give you two points there. First is um, okay, so with a quantum computer, I go from 1 qubit to 2 qubit, right? In a single qubit, I can encode two states. When I increase, say, if I um, yeah, if I increase to 2 qubits, I'll have 2 to the power 2 qubits. To 3 qubits, I'll have 2 to the power 3. If I use up to n qubits, I'm encoding 2 to the power n pieces of information. Okay. And for using just normal bits, the same equivalent number of, n qubits will require 2 to the power n bits to represent that information. So it's an exponential mismatch, right? So in that sense, if I'm doing something on a quantum computer and I want to do the same thing on using a QPU, like GPU, sorry, not QPU. If I want to do the same thing using a GPU or a TPU, I'll have to increase that many number of bits. I can just do that by, increasing the number of cores the GPU has, or just adding more nodes or whatever. But then that is an exponential increase. Say if I have 1,000 qubit quantum computer, how many GPUs am I going to need to add just one more qubit to show the increase that just one more qubit can have? It's going to be extremely high, right? So we don't have those practical cases yet. So it's just a hypothetical against argument, but I think it's a very valid one as to why, quantum computers, the scaling efficiency is good as compared to GPU. That is one argument again, but I said it's hypothetical. A more convincing or answer is not to say that quantum is doing something that QPUs or GPUs or TPUs cannot, but rather the future of computing itself is going to be heterogeneous, which means that I'm running part of my algorithm on a quantum computer, I'm running part of my algorithm on a supercomputer, I'm running part of it on a TPU, and together with I orchestrate a workflow where I get an efficient answer using all these different modular components, as compared to running everything on just say a classical computer on just on a supercomputer, right? So in that sense, rather than asking can we do something with a quantum computer that GPUs or TPUs would never be able to, instead it's better to think of it as, let's use a QPU to do what a QPU can do well, let's use a TPU to do what a TPU can do well, let's use a GPU to do what a GPU can do well. Yeah,
Thank you, ma'am.
sure. Yeah, I saw that there was a question here.
Thank you, ma'am, for solving all the questions.
Sure.
Mm. My question is, you mentioned about protein prediction. Could you please explain the flow? How to we are beginners, ma'am,
Mhm.
but we want to predict protein structure. Could you please explain the flow? How can we approach that problem?
Okay. Rather than the protein structure prediction problem, which is going to require a lot of domain specific, say, like knowledge about, say, proteins and like amino acids and everything, you could perhaps look into a graph optimization problem, which is more easy to sort of approach. So there is a tutorial which you can find in
Ma'am,
the IBM Quantum Learning platform. Sorry.
I am MBBC student, ma'am. In my PUC, I have familiar with that
Okay.
amino acids and
Oh, okay, awesome. Then I mean, I'll give you a brief answer because I have worked on protein structure prediction problem. I can answer that. So, the core. Okay, so the place we start is to consider a template lattice. So you have, say, I have a protein and I want to predict its structure. I'm going to look at it from the coarse grained perspective, where I'm treating all the amino acids as beads. Okay, so this is not going to be, you know. This is not an all atom approach, but more coarse grained bead based approach, where like the different, say, proteins like alanine, or you have those kind of modular components, right? I'm going to consider them as beads on a template lattice. Okay, and then this template lattice, I want to see whether now for one molecule, if I have a template, say a tetrahedral lattice, one molecule can go in either A, B, C, D. There are 4 sites possible, right? It can be in one of these places. So the first and second one I can fix without loss of generality. I'll just say A, B. Okay, or I can just say amino acid 1, amino acid 2. Let us take the example of a 10 bead amino acid structure. Okay, so now here I'm encoding, so the first and second I can fix without loss of generality, but for the third one, again, there are 4 possible sites, right? For the third, so I have A, B, C, D. Since it's a tetrahedral lattice, I can have like 4 sites possible. So now these 4 possibilities, I will, now this is a very simple encoding rather than a more complex encoding, but for each such amino acid site, um, I will use 4 qubits. Okay, I will say that it can either be, so I have 1, 2, 3, 4 possibilities. So each of this is a possible. Each possibility I'm representing using a qubit. So if my qubit is 0, that means that there is no amino acid there. If it is 1, I will say that the amino acid is there. So
okay.
per 4 qubits, you will only find one of the qubits to be 1, which represents that there is a amino acid there. Okay, so now this is the general sort of encoding for this, right? So I come up with this kind of general encoding, and now I know what my qubits represent. Now this qubit representation, I have to um, create into a variational. So if you use VQE to solve this, I'll have to create a variational template circuit for this, okay, for which I can use something called as an ansatz. So this is specific to the VQE algorithm, and it can be a bit complex, but just try to, I'll give you a very high level overview, okay. So this whole encoding, I will create a general state, and after creating the general state, now how to decide which bead will go where. Now here the interactions will come into play, and there are also going to be constraints, right? So if I have a bead in here at this point, the same, you cannot have the next bead coming on the same position, right? So because there will be an overlap, and you cannot have that overlap. So this is a physical constraint. So these kind of physical constraints, and also when you can so there's something called as a Miyazawa Journeyman model, you know this, right? So there's, you can have, okay, so for the protein beads, you can either use a HP model where you consider hydrophobic or hydrophilic interactions, so that's very basic. Or you can consider Miyazawa Journeyman model where you know the energies of different protein combinations, like the protein bead combinations. So yeah, now using this Miyazawa Journeyman model, you can kind of put the more interaction based constraints into picture, and using this we construct the Hamiltonian, which represents the energy of the molecule. Okay, now I will say that the structure which corresponds to the ground state is one with the minimum energy. So I will create the variational circuit which represents my randomized structure, and I will run the VQE algorithm on this state and the Hamiltonian I'm constructing, and I will minimize it using an optimizer. So a VQE workflow is you take a ansatz, which is like a circuit which represents a general state. Then you have a Hamiltonian which represents the cost function for minimization, and you will have a optimization step where you're doing the actual minimization. So I know it's a lot of okay. Let me give you a realistic map to understanding how you should implement a problem. I know I've given you an extremely high level overview, but first understand a variational algorithm, more like understand how a variational algorithm works. And you can look at this paper called a resource efficient quantum algorithm for protein structure prediction. Okay, so this will attempt to explain to you how the encoding is done. There are several more efficient ways to do the encoding as well. You can look at just nearest neighbor interactions for the energy, for basically constructing the Hamiltonian. You can look at, the nth nearest neighbor interaction. There are many sort of problem specific things that can go on here. You don't absolutely have to use a tetrahedral lattice. A tetrahedral lattice is going to give you a three-dimensional structure, but you can use a square lattice also, which will predict a two-dimensional structure, but it is nonetheless a structure that you can predict for the molecule, right? So yeah, that is the briefest answer I can give you based on what I've covered so far or not covered even. But yeah, do you have any follow-up questions?
Please take 1 minute rest, ma'am. After that,
Sorry?
I have one more question, ma'am.
Yeah.
It will may help all of them.
Sorry?
How can we how can we get internships, ma'am, in quantum sector?
Uh, Okay, you have to apply, right? You have to look at what is the requirement of the internship. Firstly, I will say that more than anything, the mindset that is important is to think that, oh no, this is too complicated for me. I don't think I will qualify, so I'm not going to apply. Don't have that mindset, first of all. Like whatever you are capable of, try to upskill from there, but apply confidently. Okay. If you don't get in when you apply, ask the people who are hiring you for feedback, and take that feedback and improve yourself. Okay, this is something that is done iteratively. But again, how you can get the internship? First, you have to apply to as many as you can, and while applying, you look at the requirements they have and try to kind of upskill in those areas. Firstly, check the previous year's hiring and see what requirements they put there. Some of them will follow in the next year as well, right? But other requirements requirements which they may have is to look at is to understand that you should look at what the company or like the academic place, what the research groups there, what they're doing, because they're going to hire you to do some related work, right? Probably it won't be, it could be something out of nowhere, which but you will not know about that anyway, right? So you look at what they've worked on, try to keep up with all that, so that when they hire you, they see that okay, this is a person who knows what I've done. I think I can take them in to work further on what I want to do. So yeah.
Thank you, ma'am. Thank you for your patience.
Sure.
Anyone?
Ma'am, good morning. And
Yes,
other than protein folding, what are the scopes on life science or biotechnology, quantum?
okay. So from like what, so there's also genome related, so RNA structure prediction. Then so basically the de novo genome assembly is one thing. Basically, wherever we can map a problem to an optimization problem, straight away that is a candidate. But aside from like the more say bioinformatics side, like work and biostatistics side, some to some extent it's possible where if you have some differential equation that needs to be solved, there are a lot of quantum based solutions for that as well, which are happening specifically in healthcare and life sciences. I think for disease, basically. Like predicting diseases, anomaly detection, right? It's in terms of QML, it is a very potent problem to look at. So anomaly detection, specifically early disease detection using say X-ray data and like existing health records, those kind of works are also going on. So yeah, there are too many things for me to list, but just off the top of my head, of course, there's also drug discovery, the like materials, basically the materials research, like some of that will translate here as well. What can be a good drug for this kind of disease? That sort of work. Yeah.
Okay, madam. Thank you.
Ma'am, is there any hardware circuits for designing of qubits?
Hmm?
Like related to quantum computing,
Hmm?
is there any hardware circuits designed using quantum computing? Or to control qubits, is there any hardware circuits?
Uh, okay. So I think maybe you're approaching this from with a more classical circuit design in mind, but here it works a little bit differently. The circuit design as of now that happens here is more for understanding what kind of problems can be encoded in different circuits and how can we create those circuits. Okay. And so in terms of how we build it for quantum computers, it is still at the stage where we are looking at, how do you, basically it's still at the level of a more efficient basis gate architecture set. So how can I have a set of basis gates that are going to implement with the lowest error possible, for example? So those kind of priorities are there, but in the future, a quantum computer which does some default adder circuits, those sort of thing, it could come up in the future, but at the moment that is not sort of the priority in terms of quantum computing, as to my best knowledge.
Ma'am, I have another question too.
Yeah, sure.
You said for swap circuits, so much of circuitry is needed to be created.
Mm.
So that we can do it in hardware, like we can design a software for that in order to encode in hardware.
So swap, okay. So here right now in hardware, the reason we do swaps is because we want to be able to implement 2-qubit gates, which are originally not possible because of the structure of the device itself. right? And that is why, so depending on the layout, the number of swaps you need will be different. So that is not something you can hard code, okay? Depending on the structure of your input circuit, depending on what the layout is, depending on the gates in your circuit, the amount of swaps you would need to do will be different. In fact, it will also be different based on how your circuit gets transpiled, like in the previous stages, say in like how your 3 qubit gates, or like if you have 3 or 4 qubit gates, how they would get broken down can potentially impact this step. So there are a lot of like it's not it's too specific to the existing parameters to be generalizable.
Thank you, ma'am.
Sure. Okay, thank you everybody. Are there any other questions? I think no, right? Okay, thank you.
On behalf of all of us, I'd like to extend a very sincere thanks to you, ma'am, for delivering such an excellent and insightful session, really. This is not just an informative session, but with the lots of patience you have handled all our questions. The questions and the interactiveness our participants have responded with is the true feedback how amazing your session is. Thank you so much, ma'am. Thanks a lot for that. And on this moment, ma'am, I would like to request you to accept our little token of gratitude and appreciation. We'd like to felicitate you for your such an amazing and extraordinary session for us today. So now I would like to call upon the head of the department of CSE, Mr. Y. Ramesh sir, and the co-convener of this fest onto the dais, and the Dean Students Welfare, Dr. Ravi Gedala, and also the co-convener of the Qiskit Fall Fest onto the dais. I'd also like to request our beloved financial officer, Dr. C.H. Vasu sir, to come onto the dais for the felicitation. I would also cordially like to invite our Dean of Academics, Dr. Merugu Sivaramakrishna sir, to grace the dais. I'd like to call upon our Administrative Officer, Dr. Muniramakrishna sir, who are also the conveners of our Qiskit Fall Fest 2025, to felicitate Janani ma'am for her such valuable insights and such a patient lecture to all of our participants.
Thank you for doing all this.
We got that road
We appreciate it.
comfortable with this one.
Yeah, yeah.
And they will do it. Everyone will be stay. Ah, they just get him on the hidden one, but it's the same. First. So confusing.
I'd like to request all the faculty of the dais and also the student organizing team to come on to the dais. Student organizing team members, please come on to the dais. Kasim, please come on to the dais. Thank you once again, ma'am, for sharing your expertise and guiding us through these fascinating topics. And everyone, let's give a huge round of applause to show our appreciation to Janani, ma'am. And all dear participants, the QR code for the feedback form will be presented on the screen. Kindly scan the QR code and confirm your attendance as well as give your valuable feedback for the session. And after filling the feedback form, you can have your lunch break. And I would like to request you to be right back as early as possible, mostly by 1, because Gyan sir will be taking the next session of the workshop by then.